This conference will now be recorded.
Okay, welcome everyone. So today we have a presentation from Med, but before we start with that, let's go through some updates about our work streams. So Alad, would you like to share with us some new information and updates?
Yeah, sure. Thanks, Ahmed. So we wrapped up an amazing OCP Global Summit um, last month, and we had presented both past, present, and future of TAP, and wanted to share here with you that on top of the existing work streams that already contributed the first specifications, we added a few more work streams, and there are different stages of forming and shaping. I would point out workstream number 3, the Precision Time API, led by Georgi from NVIDIA. Its charter and the first session of it will be kicked off either towards the end of this month or beginning of January. And we encourage the community and interested individuals to join at least this inauguration and consider contributing on behalf of yourself or your affiliation. The other work streams that we announced, the oscillators presented in the session and are soon to be providing the first specification out. But number 5, PTP servos, the design and implementation of advanced PTP servos, instrumentation, open source instrumentation of test and tooling here with Meta folks, and time sync reliability that was announced by Google, and that will be led by Google, fault tolerance and UTC traceability. So there's a lot a lot of new activities, and TAP is taking us into more implementations and into more areas we have not been active before, and I encourage everyone to join us for this ride. Also, before I hand it over to you, please review the next sessions by us. We have 2 more occurrences happening in December 15 and December 29, and I know it's holiday season, but clear out your schedule and remember to join for these sessions. Ahmed, over to you. We can't hear you, Ahmed.
Great, thank you, Alad. So let's get back to introducing our speaker. So our speaker today is Med Belhaj. Med has a PhD from University of Rennes from France. He has like over 30 years of experience in the field of telecom and datacom, and previously worked for Cisco and SGS Thompson and Nortel. So today's talk, I have that. Yeah. So today's talk will be about applications of physical layer synchronization and synchronization in data center environments. And in this presentation, basically, we'll go quickly through physical layer for synchronize, and the background about like physical layer synchronization as it was implemented in SONET and SDH, and some like primary, secondary references, synchronization chain using PLLs also will get introduced, and then some basics about understanding synchronization in Ethernet or SYNC-E, and what's the newest standards, like again around SYNC-E, the ITU G8264-.1, and also application for physical layer, like again the SYNC-E, in contrast with, let's say, layer 2 synchronization, such as like PTP and so on. So with no further ado, Med, let's get started. So let me make you the presenter, or yeah, you are the presenter. So
thanks, Ahmed. I still don't see the my ability to share the screen.
Okay, so we made you the presenter, and that means you should have a screen button at the bottom. You can press share screen there.
Beside the leave, on the left side of the leave, there should be a screen.
Mic, camera, screen.
No?
It's blocked from the system preference. Let me just quickly.
Here, I'll try to do it again.
Yeah, let's do it again.
Oops, where is Med? May have hung up. Okay.
He's restarting it, so I think it was a permission thing, most likely. So
I don't see him on the list here anymore.
he will come back. Like it just
Okay.
restarted. Also, Elad, maybe you can mention, like, we're going to have 2 more meetings basically in December.
Sure, let's go over them.
So we're gonna have one from Intel about, I think, PTM, and okay, Med is back.
Hey, Med.
Yeah, one presentation from Chris Hall is the next, and we have Kevin Stanton, which is going to bring John Eitzen. Anyways, so let's get back to Med. So your presenter, can you see it now, Med?
Yeah, I can see it. Let me just.
Great.
You got it, Med?
I got it's just a setting that I have here that is actually still.
Would you like us to present on your behalf?
Yeah, maybe it's.
Okay.
I'll have to. I'll just send it to you. Who do you want? Elad, do you want me to send it to you or to Ahmed? Or?
Thank you, Elad.
Okay, Ahmed, I just sent them to you. Let me know when.
Me?
Yeah. I don't think I have Elad's email.
Yeah. Let me quickly log in. Here. Technical. We love technical problems. So.
Hey, apologies for the delay. We'll be on. Be
Elad,
back.
check your email.
Okay.
Let's get started.
Not here yet. Here you go. All right. Okay, you should see it now.
Yes. Okay, let's get started. And sorry everyone for the delay.
All right. So that doesn't come.
Oh my God, today
It's not working. Huh?
Murphy's Law is everywhere.
Okay. I think I have something. Now it's opening. Oh, yeah. Let me try with the PowerPoint. Green. Okay, let's go.
Awesome. Let's do it.
Thanks, Elad. Thanks, everyone, and sorry for the delay. Next one, please. So a quick summary of this. So we've had, as a group, we've been attending for a few months, several discussions around synchronous Ethernet and synchronization and how it relates to the data center. Initially, I was going to present some practical results, but discussing it with Ahmed, I think it would be good for the group in general and for maybe hopefully spur some discussions about how that would apply to what we're trying to do here. So I split it into three pieces. One is a quick background. Considering we're late, I'll try to go fast, but please do interrupt me if things are not understood. A focus on SyncKey because that comes a lot, of course, as ITU and a lot of the radio-based specs use that, and how that could relate to the data center. Next one, please. So the first background, quick terminology. If you have a reference clock and then a subordinate clock, they're driving, let's say, a counter that is counting time for us. Frequency lock or synchronize is basically some form of a PLL. It could have a form of a hardware device or a software device or software program, and it locks that to the reference clock. The phase lock is basically aligning these two references or time within a given phase. So certain protocols, such as, for example, CPRI or passive optical network, have a phase that they need to all align to, but it doesn't have any meaning in terms of how it relates to time in general. And last is basically the focus of this group, which is we basically need time to be not only synchronized in phase and in frequency, but it has to relate to UTC or as time of day, as we would call it. Next, please. So in synchronization, as a kind of just a quick background, so people who are not aware would kind of follow along. It's basically if we have say 125 megahertz clock and it's off by 1 ppm from the reference we're trying to lock it to, there's two types of synchronization or frequency lock that are out there. The main ones are basically let's call it a logical one, which is kind of what is used for TSN or 802.1as, which is if you had a counter that is counting the time, say 8 nanoseconds, and we would just basically change that counter with the amount of the rate difference between the two. But there is really no physical changes to that. The second one is kind of physical layer synchronization, which is used in SYNC-key, SONET, SDH, CIPRI, and the like. And what it means is it requires a physical device, which is usually a PLL. And in our case that we gave here, the adding, we don't change that 8 nanosecond. There is methods where you could actually change the reference by using a DAC and a voltage controlled oscillator, but this is not really what we would be talking about. We would be talking about using PLLs. Next one, please. So if you look at a lot of the synchronization specs, they talk about 3 types of synchronizations. One is the external one, which is known what we use for traditional Ethernet. OTN, optical transport network, use that as well. A line, which is kind of used in SYNC-key and SONET, uses one of multiple, say if you have a node that has several ports, you would select one of these ports as your reference, and that's what you will use to basically discipline your local clock, and you use it for a transmit from this node. Just as a point of kind of clarification, if you look at some of the systems out there, some of them have multiple PLLs and they can have multiple time domains, but for the kind of simplicity, we will just consider one. Loop timing is usually what's the end node. So what it means is that it's not a pass-through, it's not like a switch or a multi-port device. It just basically recovers the timing from the other end and basically uses it as its transmit node. And it's used in things like passive optical network, PON, and CIPRI. And next one, please. So this would be, I think, a last background thing. It's important to look at these 3 components because they come up in the discussion a lot. Well, if you look at a very simplified, this is kind of top level view. You have a receive data stream, transmit data stream. Generally, a SerDes that takes a reference, recovers a clock, and you will have an external PLL that uses the internal clock, a digital filtering mechanism, and it cleans up this clock, the internal clock, and adjusts it to track whatever you received. Now, the reason you use digital PLLs instead of, say, analog is the time constant. So think of it as averaging over a very long period of time. Sometimes this is in like thousands or tens of thousands of seconds. There isn't really an analog process that will actually allow you to filter over that kind of, so they are generally digital PLLs. They've been around for quite some time. The bandwidth, like how long do you need to average, and depend a lot on the local oscillator. So think of it intuitively as that if you have a very good reference, you can basically average over longer period of time. So an OCXO is better than a TCXO, and a rubidium clock is better than an OCXO, etc. So depending on how much you can trust your local oscillator, you can basically average over a longer period of time. We would use things like called jitter and wander. For those who are not aware, jitter is really the high frequency noise, and there is ITU specs that tells you basically anything over 10 hertz is considered as jitter, and anything lower than 10 hertz is wander. Some of these PLLs have kind of some very interesting features, like they can monitor the input quality, they can switch between 2 references without causing any glitches, and they have things like they can see if there is a loss of lock or a loss of signal, etc. So those are the 3 components that are basically required or needed in a lot of these physical layer synchronization. If you have any questions, please interrupt me. Next one, please. So this is the model that is basically kind of the source of a lot of the work that is done in SYNC-key and others. So way back in Sonnet SDH days, there was this model of basically how the hierarchy of the clocks can be distributed into a system. So the recommendation from ITU is 802.3. It's the same model used for SYNC-key, but basically what it assumes is that you have a primary reference, and then you have a chain. Of course, here it's just showing basically from a timing perspective. We're not trying to model the network itself. It's just following the trail of the timing. So it's basically forward in the frequency, and each node has its own PLL and local clock, and it's basically filtering it and passing it along. And a lot of the specs that are provided are basically looking at the total noise and other properties of this model. So this model basically assumes that there is a series of kind of nodes with secondary references in between. And the worst case scenario is a chain of 60 clocks with a max of 10 secondary and no more than 20 between those secondary clocks. So the other interesting thing is there's a synchronization status message. So this status message tells, creates the trail and tells each node from the preceding node what kind of a quality it has and how far you have to go back to track to the primary reference. In the Sonnet SDH world, it was a byte in the header. In SYNC-key, it's actually carried as an Ethernet packet. The next one, please. So if you look at the hierarchy for kind of Sonnet SDH SYNC-key, there is the primary references, which are the PRC. People who are familiar with the Sonnet world, they were called Stratum, which is kind of confusing. NTP has a different definition of what the stratum is. But bottom line is that the main reference is 10 to the minus 11. And typically it's a cesium clock. There is a new definition of what an enhanced PRC is, and it has 10 to the minus 12. A secondary unit or secondary reference is usually what used to be called the stratum 2, and typically is a rubidium or double alvanized OCXO. I'm giving here some kind of idea of what kind of a bandwidth, or if you can think of it as the time that the PLL is averaging. So most of those PLLs are programmable, so these values are, but those are the values that are typical or recommended by the standard. More importantly, or kind of that have more impact on a lot of the things that are done, are basically the end node or the switches. And in there are basically 4 main categories that you can see here, going from like a stratum 3E clock. And as you can see, there are 2 clocks that are considered in SYNC-key, option 2 and option 1. And basically you can see the kind of free run accuracy and the type of holdover that is defined for these clocks. Typically 3E is an OCXO and option 1, option 2 TCXOs. Next one, please. So this just gives you an idea of what a primary reference clock. I think the reference clock that is being defined in the working group is a PRTC type A. So what you will see is the lower part. The top part is basically the characteristic of the clock as it's related to the enhanced version. Next one, please. So same thing here. So the PRTC, so the top one, which is PRTC A, which is plus 100 nanosecond, is what is defined here in the group. The enhanced PRTC, as you can see, is a fairly high performance primary reference clock. I'm just giving them here as a kind of reference point. So, and next one, please. Other protocols. So we will be talking a lot about SYNC-key itself, but there are other protocols that basically implement one form or another of basically synchronization. To say that SYNC-key is basically not the only way of actually recovering frequency and using it. It's a set of requirements and a model of what the network look like, etc. It's because it actually leveraged a lot of the stuff that is existed in SONET SDH. It managed to reuse a lot of the knowledge in the industry about the references, about the PLLs. There was some modification and improvement, but it used those things, and that's kind of one of the things for it. Now, you could do frequency recovery in many other ways without meeting SYNC-key, and you would get a fairly accurate timing for a particular application. OTN is not even, it uses a different method of kind of recovering the timing or transporting the timing transparently from one end to the next. So it's not the only way, but it's one of the ways that it's being described. So the next portion we'll be talking about SYNC-key in itself and some of the details. So next, please. Next one. Thanks. So synchronous Ethernet is just basically adding a synchronization layer, physical layer synchronization to traditional Ethernet. Ethernet, as we all know, is plus minus 100 ppm clocks. It uses the same, as we mentioned, the same hierarchy model as SONET SDH. It's only full duplex, so you require a continuous signal. The synchronization messages that we mentioned existed in SONET SDH are carried in Ethernet frame, and SYNC-key does not carry timing or phase information. So if you want to log to phase or basically have time, you need to run PTP on top of it. So that's basically the main concept of SYNC-key. Next one, please. So the packet that is basically sent in SYNC-key, two types of messages, like a heartbeat that basically just there, and an event that basically is generated if there is a something like a status change of the SYNC-key device. If you do not receive it within 5 seconds, it's considered as failed. So it uses a slow, the definition in ITU is that it uses a protocol, a slow protocol, and basically it encapsulated, there is a TLV. The first one has been defined in the original version, and the extended one, as you can see, uses clock identity from 1588 and supports enhanced SYNC-key. And it's recommended to use that one. So if we do decide to use this, the extended TLV is the one to be used going forward. Next one, please. So to say that something is SYNC-key compliant, SYNC-key considers a node as a black box. The reason I kind of went into a little bit of a description or background on the PLLs and reference and the SERDES is that kind of the point of compliance is the output of the Ethernet port. So kind of the compliance sometimes depends on the oscillator, sometimes on the PLL, sometimes on the PHY, or a combination of 2 or 3 of these ones. So just to give you an idea, next one, please. SYNC-key compliance is like these several sections. I give a reference at the end, so kind of the point is not to go into too much detail, but just to give you an idea of what kind of is required. So, for example, from frequency accuracy, it requires option 1 and option 2 and enhanced sync key, about the same for like plus minus 4.6 ppm. Duration 1 month to 1 year. Of course, the old Sonnet SDH had the 20-year for this, but for SyncKey, we talk about 1 year. Pull in, pull out, and hold in range is basically the ability of the PLL to kind of take a frequency and move it to where you want it to go. So those are the criteria. There are testers out there that I think there are a few people from Calnex here, and you can actually get testers that where there is a canned list of compliance, and you can test over each one of these criteria. So next one, please. The next set of compliance is basically about the noise, like, as we said, the high frequency one jitter and lower one is wander. And basically how much, assuming you have a kind of an ideal reference, how much noise do you generate? And that one depends on the PLL and the reference. The jitter is PLL and the phi. Tolerate, of course, in the input, if you had that much noise, how much noise can you tolerate before declaring an alarm, like a loss of synchronization or etc. And noise transfer is like how much wander noise gets transferred from the input of the device to the output of the device. Next one, please. The last set of kind of compliance points are basically these transient responses, so either short-term or holdover. Basically, how does the clock behave under these conditions, response to an input signal interruption or phase discontinuity, or losing a signal for a certain duration of time, short or a very long one, which is a holdover, and basically the ability to use other system items. Next one, please. So this is a kind of a test case. If you look at a lot of the specs that are being considered in ITU, originally or in the last few years, they've been working a lot on basically boundary clocks. There is a spec for transparent clocks, and basically it has the top portion is based on PTP. The lower portion is basically recovering the clock based on SyncKey. If you read the spec, it says that it's not mandated to be SyncKey, but it has to kind of have the same properties, or just as SDH and other synchronous standards require you to have a certain, meet certain mask at certain point of testing. So, but in general, this is a transparent clock, will use SyncKey to recover the frequency, and basically PTP will be there to do the phase. Next one, please. So in looking at the performance of the transparent clock, it hasn't defined, so if you compare it to the boundary clock is basically has 4 classes going from A to D. And if you look at the performance, the top line there, the maximum timing errors in a class A is 100, and best performing is a transparent class D, which is 15. Transparent clocks are following kind of the same performance profile, so you'd expect them to be around the same numbers. You have a constant time errors row that you see there, which is 50. I think for our group, this number has been put at around 40, but this gives you an idea of what kind of scale these devices are built for and what type of performance is required from them. Next one, please. Data center application. So data center, as we have it defined right now in the profile, is basically a fully asynchronous standard Ethernet with plus minus 100 ppm. The DCGM is a PRTC type A or class A at 100 nanosecond. The fabric or the switches are transparent clocks that are end-to-end, and the radius at this point is 5 node wide. And kind of some of the numbers, you could see them in the profile. The residence time error due to frequency offset about 10 nanosecond. Quantization, generation, and processing is about 8 nanosecond. Next one, please. So if you look at basically the, we have a data center grandmaster that is providing the timing for a set of 5 switches or transparent clocks. And we're looking at the limit at each one of these points. So this is what we have right now. So going from there, we could stay the same or kind of pick one or two or both. So the next option would be, for example, using just logical synchronization, which is similar to what 802.1a's does, which is let's figure out the rate of each one of these or the fractional frequency offset from each one of these nodes compared to a grandmaster, and we will basically correct for the frequency in each one of these. So next one, please. So if we do that, then it would be a software-only solution. You can do the frequency disciplining in software. I think the oscillator group is looking into some of these things. But for example, a very simple way to improve the performance would be to kind of pick TCXOs for the switches, and the maximum residence error would become half a nanosecond max, and that basically reduced the performance, and basically the timestamping errors will be the dominating factor. Of course, that also helps with basically the frequency discipline, the characteristic or the averaging that we would be able to use for a TCXO on the switches would be a lot better as well. Using a logical synchronization has some advantages over kind of hardware PLLs. Of course, there's no gain peaking, and you can switch references very quickly because if you have a PLL that has a very long time constant, switching from one to the other will take a little bit of time. However, of course, if you have hardware PLLs, they are very robust because they don't, unless you lose really the link, there is no way for you to lose the synchronization. They also have their ability to monitor the signal and the quality of the frequency, and they're not dependent on any traffic or packet content, etc. And also, if you do a kind of software-only solution, if you need to interface to equipment that is requiring a physical sync, like radios, use their line connection to basically drive the RF part. So they make a lot of assumptions, and some of these assumptions, depending on the equipment, is basically that the equipment does support some form of frequency, like physical frequency lock. Next one, please. So this is just going over the physical. Yeah, thank you. So the physical synchronization, or basically would be leveraging sync key or a subset. As I've showed before, there is tons of criteria to meet sync key. Some of them might be applicable and not applicable. Of course, when you use frequency lock and hardware, the error due to residence time, etc., is pretty much almost nil. So it's really just the phase errors, the asymmetry, and any issue, any kind of errors in the timestamp itself. What that means is that now, if you do this, you have to basically incur the cost for every switch that it has to basically now support a compliant reference oscillator. So you could choose a TCXO, for example, and a PLL. They're not very expensive if you assume a 32-port 1RU switch. It's around $1 or $2 per port or less. So, and also the additional work is that you need to qualify the grandmaster for the data center and the DCTCs. They all need to be qualified to be a sync key, or if we define a subset, then we have to make sure that that subset is basically compliant. Now, one thing that is kind of, I think, I would really like to kind of hear people's thought on this, is that to basically leave the end nodes as they might be. So meaning that ensure that the grandmaster and the switches can handle the physical layer synchronization or synchronization. However, do not burden that cost into the end nodes, meaning that we can have a cheap node that has a sub $1 oscillator and works as with the performance that comes with that kind of decision. But if we wanted to basically put a radio equipment that has a high-end oscillator and want to do sync key, then it burned only the node that needed. So you get the best of both worlds, where basically the incremental additional cost goes into your switches and your grandmaster, which is already almost there, but leave the nodes to basically only use this if they need to. So the next slide, please. And this gives an example that you have two grandmasters and the switches or the fabric in between uses TCXOs and PLLs to basically have a frequency lock on the one of the two grandmasters. And basically using that, we can have anything that is not the end node is synchronous. And the end node itself, depending on the application requirement, we could choose to have it as a MEMS or a crystal oscillator, or TCXO and OCXO, whatever that might be, and be able to kind of have it as a performant or as cost effective as we want it to be. And I think the only other slides are basically reference slides for anyone who would like to look at more details on this, and I'll open it for any questions or comments. Or
let's see. There's one from Dan. Dan Biederman.
Sorry, go ahead.
Dan Biederman, would you like to sound your question? I can read it out loud for you. Are there EMI issues with running sync key in the data center? Large number of components and wires oscillating at the same frequency. That's a question to you, Med.
There are certain constraints, and you're right. point them out. So when you basically choose the PLLs, there is some amount of care that needs to be taken. So, and even basically certain PLLs will mandate for you to have, if you need 2 clocks of certain frequencies, they will tell you which frequency to put on what port. So there is definitely, so that's a good question. There is a cost associated with that. And basically it's a balance between when you choose them, you have to kind of pick the PLL, pick the reference. In general, PLL vendors have been working on this for a while. They'll give you the list of TCXOs and OCXOs that they work with, some recommendation in terms of how to implement that, how to isolate it, and even your frequency plan. So if you have a SerDes that require 156.25 megahertz clock and another one that requires 162 point something, then it gives you some information. But you are correct. You need to take it is not basically just a kind of plug and play. There is some care that needs to be taken.
Okay, Ahmed, would you like to go next? Ahmed, you wrote a question. You wanna? How is it compared to White Rabbit? Says Ahmed.
Okay, that's a very good question. So White Rabbit uses actually frequency lock. However, their frequency lock, I don't know if it's for historical reason that it came before SYNC-key or not. You know how there is a list of these requirements that make SYNC-key SYNC-key. I don't think that White Rabbit will hit a few. I think gain peaking and a few other criteria will not work. I know the folks from Seven Solution. I don't know if any one of them is on the line, but they were actually looking into doing certain things with the SYNC-key to be compatible, but it is not. So locking onto a frequency using phi is something that you can do in lots of different ways. SYNC-key is very specific, is those 12 or 13 criteria that I put on the list. Moreover, White Rabbit has also additional things where it actually is reducing the sampling errors. So the phase, it uses a technique to basically not only calibrate the delays, but also sample the delays based on this fractional value. So they're concerned a lot with the phase between the clocks. So one component, which is locking a frequency to 1, physically locking a frequency to 1, is the same as similar to the SYNC-key. It would not, as far as I know, it would not hit all the criterias that SYNC-key gives. But it's kind of same. So if you look at, for example, something like PON also lock on the frequency and can get very accurate because the OLT moves the phase at a fairly high rate, and it actually always lock on the signal within a few nanoseconds. That only happens because it knows that the ONU has a frequency lock, but it's not necessarily SYNC-key. It doesn't hit that one. So hopefully that makes sense.
It does, at least for me. And yeah, 7Cs had a great presentation overview, but I don't think they are present today.
Okay.
Okay, let's open the microphone for more questions to Med. No further questions, looks like, Med.
Okay, thank you. And in time too.
It was a great pleasure having you.
So fast.
Very useful, at least for me. And we will wrap it up for today. Find it online, and we can take any follow-up items on the next call.
Excellent. Thanks, Ella.
Thank you.
Take care. Bye.
Bye.